And we're back. So today we will continue and finish up. This is the last class of the semester. We'll finish up our material on radial basis function. Before we begin, I'd like to mention some administrative bits. The final project concerning SVMs and optimization has already been out on the Blackboard. It will consist of two components. A presentation on Monday, the 4th of May at 6 p.m. You'll each be given half an hour to present. That's the scheduled final exam period selected by the registrar. And the final project itself will be due on Friday, the 8th of May at 8 p.m. So where we last left off, we talked about Lloyds algorithm, and Lloyds algorithm was an improvement on the radial basis function for classification and regression based on the idea of introducing a number of centers instead of using every in-sample point as a center. And so this involved two steps in an iterative alternating algorithm where you start out making an initial cluster assignment. You then calculate your cluster centers, and then you fix the cluster centers, and subsequently, after fixing them, you reassign the cluster membership. So then after you reassign the cluster membership, you go back to the first step, keeping your cluster new cluster assignments fixed, and then you update mu sub k. And on each iteration, it's getting smaller and smaller. Because if you look at this step for the cluster assignment, well, it's choosing the closest center. And so this expression is going to get smaller after each round because this expression is going to get smaller. And so you keep doing this until convergence, and you're going to converge upon a local minimum because you have two finite sets of things. You have a finite set of data points, in sample points, and you have a finite set of cluster centers. Okay, so let's continue on. And we'll take a look at Lloyd's algorithm and compare Lloyd's algorithm, which is a form of unsupervised learning based purely on the feature vectors. And we'll compare that to support vector machines. Now, the important part is the two are entirely different, but they're related because you can have a support vector machine using radial basis kernels, right? These radial basis kernel functions. And so for RBF, you get your data points, and you look only at the inputs, at the feature vectors. You initialize your center, your mu sub k's, and then you run Lloyd's algorithm, and the result is your set of centers here. And so in this example, we assume that k is equal to 9 centers, and we're going to make a comparison between that and the same data set on which we ran support vector machine. We had 9 support vectors. So if we look at that, well, we see the following set of centers as a result of Lloyd's algorithm coming to convergence. And we can see here that these centers are kind of representative of the data. So this center, it looks like it's representative of those data points. This center captures those data points. That center captures these data points. This center looks like it's capturing those data points. Here we have this center capturing those. This one capturing those. This one looks like it's capturing these. This one certainly capturing these. This one looks like it's capturing those. And so some of these clusters might straddle between the positive examples and the negative examples. And again, it's important to note that we're not examining the ground truth class label here. We're only looking at the features. And certainly if you look at the support vectors, well, these support vectors, you notice some are positive and some are negative. And these support vectors, the weighted sum, define our hypothesis. And so we have 9 support vectors, and the support vectors are representative of the data points in the sense that these support vectors determine this plane, right? And this hyperplane, separating hyperplane, determining the max margin hyperplane. So they're kind of indicative of the data, whereas the centers are indicative of the data in the sense that all of the data are within clusters that are some combination, if you will, you can determine from these centers. So this is a side-by-side comparison between support vectors and radial basis function centers just by using the same function, the radial basis function, In the case of support vector machines, it's a kernel, radial basis kernel. In the case of radial basis Lloyds algorithm, it's the cent using radial basis function to compute these centers, right? We have very different behavior, even though we have the same radial basis function. And again, Lloyd's algorithm uses this radial distance here. So using something very similar in both cases, with a little bit difference in how you use it, you get some dramatically different types of behaviors. But they're both representative in a different fashion. Okay. So how do we solve for Lloyd's algorithms using these centers? Well, we have our expression here, and this gives us n equations, our expression for h of n, and we want it to be approximately equal to y of n. And now remember, we have k centers, where the centers are mu, the cluster centers. And so this means we have n equations, because we're evaluating this h of x on all of the big N many in-sample points. And of course, this has k centers because it's the cluster centers, and there are k clusters. So this gives us n equations in k unknowns. So it's rectangular and not square, and k is less than n by definition. That's why we chose the centers. So again, we can solve Lloyd's algorithm, this W vector, using radial basis functions by composing, again, our phi matrix, our set of coefficients, our evaluation of the radial basis function, right? Each row is an equation, and each column is one of these unknowns. So this is the first unknown corresponding to mu1, and this is the kth unknown corresponding to mu k, and then this is the first equation corresponding to x1, and this is the nth equation corresponding to h, our hypothesis evaluated on x big N, the nth in-sample point. And so if this is invertible, which it is not because it's rectangular, then we can actually solve for the w that gives our h of x, that makes our h of x equal to our output ground truth label yn. And so to do that, well, what do we have here? We have phi times w is equal to y. So how we solve this? We left multiply by phi transpose on this side, phi transpose left multiplying y. And we do that because we know that phi is not invertible because it's rectangular, it's n equations in k unknowns, but phi transpose phi certainly is invertible because that's rectangular, it's square. And so here, this phi, it has a rank of n rows by k columns. Phi transpose is k rows by n columns. So multiply these together. Phi transpose phi is going to be k by k rows, k columns, and that is certainly invertible. So once we do that, okay, we then left multiplied both sides of equality here by phi transpose phi quantity inverse. So we left multiply that on the left-hand side of equality. So that's phi transpose phi w. And we also left multiply other side of equality by our phi transpose phi inverse. Okay. So inverse times phi transpose. Forgot the phi transpose. That's phi transpose. So that gives us, on the left-hand side of equality, that goes to identity, and we're left with w times identity, which is w is equal to phi transpose phi inverse times phi transpose y as our expression for w. Okay, so we can certainly solve for the weight vector w that will give us the right w for this hypothesis so that we can mimic the ground truth class labels. Okay, so let's take a look at a graphical representation of our radial basis function. And we can think of this radial basis function evaluation on each one of our centers as a type of feature, right? It's a nonlinear transformation, which a feature is, a phi function, and it depends on our in-sample data. And this is no longer a linear model because this is a nonlinear function. And so here, our features are dependent on the data set. And so here we have our data, and then we have our radial distance relative to the centers. And you can think of the centers as parameter. Yes, you use Lloyd's algorithm to determine our mu's, but you can think of them as parameters to this model that you arrive upon from Lloyd's algorithm. And so here you have your radial function, and you pass it through your nonlinear exponential, or Gaussian, if you will, and then you combine them as a weighted sum. So in this particular case, you add in a bias term, our hypothesis, the value of the features depends on the data set because it depends on the radial distance from these centers. And so if you have a large distance between your data point and your center, well, that's not going to influence your model very much, and that feature has more influence if you have a smaller distance between your data set and your centers. Okay, so let's compare a neural network to radial basis function network. And your radial basis function network is kind of like an SVM. The first layer you can think of as selecting the kernel, right? A kind of Gaussian kernel, this e to the minus of some function of x, the radial distance. So this first layer acts like the kernel, and the second layer takes that kernel now in this feature space, if you will, and it combines them in a linear model in feature space. So if your distance is large, your distance between x and your center, then the contribution is going to be very small to this hypothesis from that particular feature because of that exponent, negative exponent. It's going to be very close to zero if you have a large negative exponent. In the case of a neural network, well, what did we have? We had W transpose X, and then we had our nonlinear function, our squashing function, our theta, like tanh or sigmoid or what have you. And these features are learned by backpropagation. So we're essentially using our weighted sum to effectively kind of turn on each one of these features that are combined through some weighted combination. Okay, and so here in the neural network, our features are learned through backpropagation, whereas our features come from the kernels through a linear combination for support vector machine. Okay, and so now we can treat this gamma, we can treat it as a parameter to be learned. And as such, we have our weight vectors, W, which is our linear combination that we need to find. And we know we can find these W's solving for the pseudo-inverse. And then this gamma, once we know what these W's are, we can find this gamma using gradient descent for the single variable. We set the gradient equal to 0, and we just find through gradient descent what this should be. And so we can solve for this gamma using an iterative approach similar to Lloyd's algorithm. And this is a special case of mixture of Gaussians and a special case of expectation maximization, because we have our Gaussian part, which is e to the minus some exponent, and then we have our weighted combination of those Gaussians. Okay, so what do we do here? First thing we do is we fix gamma, and then we solve for our W's using pseudo-inverse. And then once we solve for our W's, well, once we solve for our W's, we then fix our W's, and then we use those fixed W's in this new version of the expression to minimize the error with respect to gamma. And then we keep alternating back and forth until we get convergence. Okay, and so here we can certainly also have a different gamma for each center, because you might want to scale this radial basis function differently depending on which center you have. So you can have them, some are wider in terms of the interpolation, and some are more narrow in terms of the interpolation. And we can still solve that by here solving for each one of these gamma k's, and it still is a very feasible problem to solve. Okay, so let's take a look at a comparison between radial basis functions and support vector machines. And so in a support vector machine, well, Your W vector is just a weighted sum for all of the support vectors, those vectors for which the alpha our Lagrange variable is greater than 0. And it's just this alpha n yn times this kernel evaluation, the inner product between our input 8x for your h of x and each of those support vectors plus the bias term. So this is our support vector machine using the radial basis kernel. Now, for straight radial basis function, right, that composes our h of x, which is just sine. Okay, well, sine can take this score, and that can be either positive or negative. It'll return +1, -1. Okay, so we can solve support vector classification. It's kind of like bootstrapping classification from regression, because this would be our regression, a radial basis function. It'll act like our regression, and it'll certainly try to match the +1, -1 assignments for the ground truth, +1, -1 labels. And then we take this expression using centers. And so the centers, if you will, in radial basis version of classification, they serve a similar role as the support vectors. They determine what the hypothesis is. These centers you can think of as parameters for this radial basis function classification approach. And so here we have, for support vector machine, max margin with kernel. We use quadratic programming for support vector machine, but we can get a similar classifier using radial basis functions, Lloyds algorithm, and pseudo inverse in maximization to try to find the gamma and the W and the mu's. Right? So the W and the mu's are from Lloyds, and then we try to find the gamma using that alternating approach, expectation maximization. Okay, and so we can take this radial basis function and we think of it from purely a regularization standpoint. And if we take our version of the hypothesis, looking at the squared error loss, that's for minimizing in-sample error, we can add a smoothness penalty where we evaluate how smooth, using second derivative, how smooth that hypothesis is over all of the support. And we're making an assumption of one dimension here. And so if we do that, okay, what we end up with is something that looks like radial basis function. So we have a one-dimensional function, and you're trying to make a smooth approximation. And we're going to use function approximation, which has a smoothness criterion, and we add that smoothness criterion using regularization. So we try to minimize in-sample error with our squared error loss, and then we also add to that a penalty term or regularization that penalizes for non-smoothness. So you can have smooth solutions. So your smoothness can be taken as a constraint on the second derivative, right? That's the rate of change of the rate of change. And you can generalize this as the kth derivative. So here we have the kth derivative over all orders of the kth derivative. Then that is a smoothness for the entire function. And so we talk about squared error because we only care about the magnitude relative to the ground truth class label, and we integrate this over the entire support. And if you do this, well, this gives you the radial basis function. The radial basis function, when we look at the best interpolation, this is the Gaussian. It makes sense that the Gaussian is the best interpolation. The sum here looks a lot like the Taylor series expansion for the exponential function, right? And so if we try a different hypothesis, this expression gives us the radial basis function. Okay, so with that, we will end there. And this is the final class. And I thank you. Granted, this is a required class for the graduate degree, but I thank you nonetheless. I appreciate all of your hard work throughout the semester, particularly as we deal with this shelter-in-place, stay-at-home as we go through this COVID-19 pandemic. I appreciate all the hard work you have done throughout the course of the semester. And so I look forward to your final project submissions. And as always, please stay healthy, stay safe, and I will see you later.